Parent functions and transformations. Okay, today we're gonna learn another one of my absolute favorite thing, parent functions. Okay, so speaking of families, this is a good segue, right? Functions also have families with parents and offspring, I guess, right? So a family of graphs are basically a group of functions whose graphs have similar characteristics. So for example, all linear graphs, all linear functions have the same types of graphs, so they are in the same family, right? All quadratic functions have the same looking graph. They all have parabolas as their graphs, so they are in the same family, and so on. The parent graph, or the parent function, is basically the simplest graph in that family. So for example, if we look at the linear functions, y equals x, that's the most basic function that you can get. That's the parent function. And then anything else is an embellishment of that. So you take y equals x, then you make it into like 2x plus 1. That's an embellishment. Those are the other members of that family. So the parent graph is transformed to create other family members of the graphs. Right. So we're going to start with 4 types of families. Okay, 4 parent functions today. Okay, and then eventually, this is why I love algebra 2, is eventually we're going to get into more families and more and more. And then by the end of algebra 2, you will have been introduced to a wide variety of functions. So let's start with the constant function. The way this looks is you have f of x equals a. Now look at what this says here. A, that symbol, and r. What that says is a is a member of the real numbers, the set of real numbers. So that symbol, right, it means like is a member of this set. So f of x equals a, that means, you know, f of x is a real number. So for example, you know, you can have, for example, you know, f of x equals 5, and so on and so forth, okay? All of the graphs for this type of function, it's like y equals 3, y equals negative 2, are all horizontal lines. Okay. The domain is always going to be all real numbers, and the range is always going to be one value. So y equals whatever the number was. So in this case, y equals a. Okay? So if it's f of x equals 2, y equals 2. Okay. Next type is the identity function. The identity function is f of x equals x. And you can figure out why it's an identity, right? Because if you have y equals x, when x is 2, what's y? 2. When x is negative 5, what's y? You see how it's like an identity, right? It's the same identity. So that's why there are identity functions. Here, this is basically where you get, you know, like all the linear graphs, right? Okay, the domain of these is what? All real numbers. And what about the range? All real numbers. Because remember, all of these extend outward in 2 directions. Okay, next, one of my absolute favorites, absolute favorites, this is the absolute value function, okay? The absolute value function looks like, you know, that's how the function looks, and the graph looks like this. So basically, the way this starts, you don't have to draw this, but I'll give you a little bit of a behind the scenes. So this starts out as y equals x. So imagine, you know, don't look at this part that goes up. This starts out as y equals x. You see how this part to the left is where the y's are all negative? When you put something in an absolute value, what does the absolute value do to it? So all of the negatives now become positive, right? So everything that was negative here now transforms upward and becomes positive. That's what the absolute value does to a function. There is a vertex here. Okay, that's a closed circle. Okay? So the domain is all reals. And what's the range for this one? Greater than or equal to 0. Okay. Next, we have quadratic functions. Quadratic functions are when you have an exponent of 2 on the variable, right? F of x equals x squared. Oh my God, there was a glare and I couldn't see you.
Hi, how are you?
How are you?
How are you?
God, I'm okay. This is like a lifetime
I know,
ago.
4 years ago.
Oh my God, has it only been 4 years? Oh my gosh,
Yeah.
wow.
Yeah.
How you doing?
Good.
Good.
What are you teaching right now?
Algebra 2 honors, right up your alley. Yeah.
Oh my God.
Yeah.
4 years. So funny.
It's so funny.
Totally.
Yeah.
We don't want you.
Okay.
Yeah.
All right.
Be good kids.
Yeah. Yeah.
Oh my goodness.
Wow. Okay. So quadratic functions all have graphs that look like that are parabolas. So domain is all real. And then y is going to be either greater than or equal to, the minimum or the maximum. So 0 here. Okay.
Wait, but it could also be negative, no?
It could be like flipped over downward, and then the range will be like y is less than or equal to a number. Okay.
Wait, it has to have an exponent.
To be a quadratic function, it has to have x to the power of 2.
So it has to have 2.
It has to have an exponent of 2 on the x. Okay, so those are the basic families of functions. Now, you can take these parent functions and you can make embellishments to them. Of course, in math, we don't call them embellishments. We call them transformations of graphs to change them into, the cute little functions that we know. So a transformation, right, may do various things. It could flip the graph over horizontally or vertically. It could, move it left, right, down, and so on. So take a look at this one here. Take a look at this. The one to the left is the parent function. And then do you see the one to the right? It has been moved over and down a little bit. That's a transformation. Okay, so let's take a look at how we graph them. In the beginning, we start graphing them with, a table, and then you're really gonna, you'll be experts, and little by little, it won't be as necessary anymore. Okay, so we're gonna talk about f of x equals absolute value x. So we're gonna plug in values for x and get values for y. Okay, of course you're free to plug in any number that you want, but then there are some wise choices and, that will give you a better look. You always want to plug in 0, okay, because that's a good number to have, right? That's the y-intercept. And then you always want some negatives and some representative positives, right? So I like, for example, -2, -1, 0, 1, 2, right? You've got some positives, you've got some negatives, you've got the 0. You can plug in -754, but who wants to do that, okay? So now we're going to plug the values into x over there. So -2 becomes 2 and 1 and 0 and 1 and 2. Okay? So then 0, 0, 1, 1, 2, 1, 2, 2, and so on. Okay? Here and here. So that's how that looks. You can put the arrows or you don't have to put the arrows. It's up to you. All right. So you see how in the right-hand side, this has a slope of 1. Remember, it came from y equals x, right? And then remember, the other side too used to be y equals x, but then it flipped up, right? It got reflected upwards. So now what's the slope over there? -1. So even though it would have started out as y equals x, it now sort of became y equals -x. And I think we talked about this before, that you can actually write a piecewise function for this, right? X, -x. Because it's one function on one side, one function on the other. Okay. Let's talk about translations. A translation just moves the graphs without doing any other changes to it, up, down, right, left. It's like if I were to take a chair and physically just displace it left, right, up, down. I don't make the chair bigger, smaller, wider, narrower, or flip it or turn it, nothing. That's a translation. Now, how can we show a translation in the function? When a constant k is added to the parent function, the result becomes f of x plus k, and the graph moves up k units. When you have a constant k subtracted from a parent function, the result becomes f of x minus k, and it's translated down k units. So it all starts from the parent function. You take the parent function and you add a number or subtract a number from it. So take a look at this next one. You have f of x equals root x plus 3. Where's the parent, not root x, absolute value x. Where's the parent function? What's the parent function of this one? F of x equals absolute value of x. That's the parent function. Now what have we added on top of that? The plus 3. Because it's a plus 3 on the outside of the function, this moves up 3 units.
So it starts at 3.
Yeah.
Does it have to be K? Like K is the zero?
Yeah. K is the symbol that goes for that, okay? So now, take a look at what happens. Take a look at what we did here. Without you knowing, we did a lot of things here, okay? First, remember how I highlighted that before as well, right? That's a closed point right there. That's the vertex of that. And it was always at the origin, wasn't it? Now when this graph moves up 3, it's like everything in the graph moves up 3. So that point moves up 3. 1, 2, 3, 0. Now, you can do a table for this, or once you know what an absolute value should look like, you can just go from there. Because look at what else we did. We said there was a slope of 1 here and negative 1 there. So from here, can we draw, right, a slope of 1? So up 1 over 1, up 1 over 1, and so on. And that's how that function looks. Do you see that? So we used our knowledge of absolute values, translations, and that's how we did that. Look at this one. What does this do? Moves it down 4. Okay, 1, 2, 3, 4. Okay, so from that, again, you got a slope of positive 1 and negative 1. So I go up 1 over 1, up 1 over 1, boom, boom. Now, that's really all the work that you should have to do for this. That's how quick it should be to graph these. Now, suppose on a test or a quiz, I ask you to also label 3 points. Then you would just label, like this one would be 0, comma, negative 4, 1, comma, negative 3, negative 1, comma, negative 3. Okay? If I ask you to label. Cool? Because we need to, because it can't just be like, you know, random points. Okay? All right.
Wait,
Let's.
how do you know what points to graph after the negative 4?
Because it's got to have a slope of 1. Okay? So 1 up over 1.
Why would it not be that? What is the...
Okay, so remember when we graphed the absolute value first with the table, we got this. And then you look and you're like, oh my God, look, it's got a slope of 1, right? Which we also knew because I had said this is the line y equals x, so it's got a slope of 1. So all absolute values, their parent form, have a slope of 1 and negative 1. So from that, that's how you're going to start. Now, sometimes that might change, but until then, that's what's going to happen. Okay. Now, so this is how you move up, down. Now, how do we move right, left? When you have a constant h this time, h moves it right, left. is added to the parent function, what you get is f of x plus h. See, now it's f of x plus h. The h is now inside, okay, with the x. Okay? So, this one though, it goes in the opposite direction. When you have x plus h, it moves to the left. Okay? When you have x minus h, it moves to the right. Okay? It's kind of counterintuitive, but is it really? Let's see. So take a look at this one. Just by looking at this, f of x minus 6. You see how the 6 is inside with the x? Which way does this graph move? To the right 6 units. Okay, so now instead of it being at 0, 0, right, that vertex being at 0, 0, where is it going to be at now? 6, 0, and then from there I still have a slope of 1 and a slope of minus 1. Okay, let's see how it does affect the table. That's what I was going to show you guys next. Okay, so you can totally do it without the table. Now, if you kind of forget or the table is, you know, your thing, here's what you do. You have x and you have y. So let's pick a number for x. Let's pick 5 for x. Okay? What would y be? 5 minus 6, 1. So look, at 5, it's 1. So you could still do it. The thing, though, is if you just pick -2 to 2, you're not really going to get this action here, right? So you kind of have to know how that plays out, okay? Okay. Oh, look at this next one. Where does this next one move? Where does the +2 move it?
Left 2, down 4.
Left 2, down 4. Good. So it's at -2, -2, -4. Isn't that fun? And then from there, you still have a slope of 1, 1. 1 and -1, right? So up 1 over 1, up 1 over 1. Boom, boom. Okay? Isn't that fun? Right? So now you could just draw like absolute value graphs no matter where you are. Okay. Okay. Reflection. Reflection. Okay, now that we know the word reflection, we're not going to use that other word anymore. So a reflection flips the graph over a line of reflection. But now, like I said, now that we know the word reflection, we're no longer going to use the word flip. Now it's reflected or reflection. Okay? When a parent function is multiplied by -1, the result is negative f of x. So you have a negative outside, and it is a reflection in the x-axis. What does it mean it's a reflection in the x-axis? It means, okay, so this is the x-axis. Pretend that's a mirror. The graph gets reflected along the x-axis or in the x-axis. And then when the variable is multiplied by -1, you have f of -x, and it's a reflection in the y-axis. Okay, so let's take a look at how this works. Y equals negative absolute value of x. All this is, because of that negative, this is a reflection in the x-axis, right? The negative is out front. It flips, I know I'm using the word, it flips like this from top to bottom and vice versa. So, how is it going to look? Here, this time, do I go up 1 over 1? I go down 1 over 1, down 1 over 1. Can you also do this using the table?
Yeah.
And you would get the same exact thing. Right? Because let's say you have -1. Now you have -1, which is -1, which is what we got. If x is 1, you have -1, -1. Yes. Can you wait 7 more minutes?
You don't have to use the table, right?
You don't have to use the table. But, mark down the points if you do it. Okay, what does this do? What?
Moves it down.
Hang on, I'll tell you that. Okay, moves it
Down 3 into the
down 3
The left one.
to the left one, and there is a reflection. Okay, so left 1, down 3, and there is a reflection in the x-axis. Please just don't just say a reflection, say in the
We
x-axis.
have to write that every time?
If I ask you what the transformations are, that's what you have to tell me about the transformations. So let's take a look at what we're going to do here. Let me plug this in. So where is the vertex going to be? That point at the, so it's left 1, down 3, right? So left 1, down 3, negative 1, negative 3. Right? Because we went left 1, down 3. Right. But now, before the flip, this would have been pointing upwards, but now it's going to point downwards. So now I'm going to go down 1 over 1 and down 1 over 1. Okay. Okay, what about a dilation? A dilation basically shrinks or enlarges the figure proportionally. And when you think of a dilation, look at me for a minute. Imagine you've got like the absolute values, right? So like, like that absolute value graph. Now imagine here, you've got like a piece of string attached to it or something. And imagine you hold on to those strings and like you pull up or you compress. That's what we're talking about, okay? A vertical stretch or a vertical compression, okay? Yeah. So we talk about, when a nonlinear parent function is multiplied by a coefficient, and the coefficient is greater than 1, then we have a vertical stretch. When we multiply by a coefficient between 0 and 1, it's a vertical compression. So look at this one. Multiply by 3. Okay? 3 is greater than 1. So is it a stretch or a compression? Stretch. So this is a vertical stretch. Now take a look at what happens. It hasn't moved up, down, right, left. So the vertex is still at 0, 0. But now, because of the 3 here, I'm going to say that the slope is 3 and not 1 anymore. So I'm going to go up 3 over 1 and over 3, up 3 and over 1, okay? So like this. You see what it does? And you see how it's like stretched upwards, right? So it became narrower. What about the other one? Is it a vertical stretch or a compression? Compression, because since this is between 0 and 1, it's a vertical compression. The vertex stays the same, and now the slope is 1 over 2. So I go up 1 over 2, up 1 over 2, and you see how it looks like it's been, compressed, so it's wider, okay? All right, so we will stop here today. You have homework from the book. We've covered everything you need for the homework from the book for tomorrow morning, bright and early. Okay, all right.